We will start actually showing you today how to build detectors and shielding and whatever else you want to put in your detector simulation or your Geant4 simulation. And we'll start by talking about the materials and how you can put them together. So we'll discuss how materials are designed within Geant4 and then show you how you can define them with all of the various combinations that are possible. And then the easy part is at the end, where you can actually not do any work at all, but we'll save the best to last. So in Geant4, the materials are pretty much organized like those in the real world. So we can start at the basic level with isotopes and define those. And from isotopes, you can build elements. And from elements, you can build molecules or compounds. And then from there on, you can build any kind of mixture you can imagine. So you can have solid, liquid, or gas, but we can't really do a plasma. Okay, so maybe if somebody works really hard at it, there's a way to do it. But it would be difficult in Geant4 to do a real, true plasma. We can define pressures, temperatures, and densities for all of these materials. And once you have all of these, you can put together pretty much anything. So usually most people will start with the element class. So there's a class called G4 element, and all of them are available. And then you can build a compound or a molecule by assigning 2 or more instances of the element to the material class. And I'll show you the code about how this is done. Once you have the materials, then you can mix 2 or more of those, and that is also a G4 material. You can build a material from a single element. You don't have to make a mixture, but you can. And you can define your own element. So we talked about isotopes. There is a class in Geant4 called G4 isotope, where you specify the number of protons and the number of neutrons, and then you can build an element. If it is not a standard element, you can build it from the isotope. First thing you have to do is set the density. Everything else is optional. So you have the option to set the state of the material. So it could be a solid or a liquid or a gas. Temperature is defaulted to standard temperature and pressure. So it is 273 Kelvin. Pressure defaults to 1 atmosphere or 100 kilopascal. So all of these are set by default. You normally don't have to set them, but you can if you like. In most cases, it doesn't really make a lot of difference. Sometimes the electron density is changed if you change the temperature. The temperature is especially important if you're doing anything with neutrons. But most of the cases for other particles, the temperature doesn't matter. Now, this is the normal stuff. So when you set the defaults, these are materials at normal temperatures and pressures. But you can really do some interesting things. You can define gases which are far from standard temperature and pressure. You could, for example, define a high-pressure solid. So if you have a diamond anvil or something that makes really high pressures, that can be done. And you can have such things as low-density liquids. And in this case, that would affect the electron density and therefore the ionization. So when you're doing things like this, you should note and be careful that the defaults are not used, but in most cases you will be using the defaults. And finally, after all of this, you can decide that I want something from the National Institute of Standard Material Database. In this case, the materials are predefined, the pressures are predefined, the temperatures are predefined, so everything is there for you. But first we go through the hard part of defining them yourself. So let's look at some code. And we'll start with just a single element material. So the first thing we do is set the density. In this case, it's 4.5 grams per cubic centimeter. And we'll talk about units later, but Makoto actually already mentioned units. Okay, so you already know about that. But just to remind you, you have some number, and then you will multiply it by this string. In this case, grams per centimeter cube is a string, and that tells you what the density is. You always have to have this here. Then you have to define A. So this is the grams per mole of the material. And now you're ready to go ahead and set the material. So this is a single element material, and we're going to give it a name. So the first argument of the material constructor is the name, and we're going to call it pure titanium. You could call it something else. Set the Z, it's 22. Set the atomic number, so 47, and then set the density. So that's an easy first step. You're also going to probably want to define at some point vacuum. So this is an important one. You do not want to set the density to 0. Okay, Geant4 has a problem with zero density materials. What you have to do is set it to a density which is very, very low. And so there is a special material that you can use, and probably the safest and easiest thing to do is to make sure that you have an instance of the G4 Nist Manager. So this is a manager that accesses all of the predefined materials, and there are hundreds of these, for which people know very, very well what the material composition is and the densities. And they have already defined something called galactic density. So this is galactic hydrogen, and that's density close enough to 0 that you can use it for vacuum. Or if you want to define a vacuum inside your beamline and you know what the pressure is in the tube, you can do that as well. But it cannot be 0. Another thing that you cannot do is use average materials. So you cannot define the atomic number to be a fraction. It must be an integer. And normally for electromagnetic, this is fine because it just takes the Z, and the Z is actually a floating point number. But if you get to hadronic interactions, then it has to know what the particular isotope is. And so if you define an element that has a fractional charge, the hadronic code doesn't know what to do. So this is not allowed. Now we've defined elements, let's go and define a molecule. And let's start with water. So here we set the grams per mole at 1.01 grams per mole. And we're going to now define an element. And we'll call it hydrogen. So set the Z, set the A. And now we're going to go ahead and define oxygen. So A is 16 grams per mole, Z is 8. And as I said, you can change the name here to anything you like, but these strings are required, so you have to have some kind of name. And then the second argument is the symbol. We usually stick to the standard symbols for the elements, but you can make the name anything you like. Density, here, we can set that to 1 if we like, or we can make it high density or low density, but for now we set it to 1 gram per centimeter cubed. And now we're ready to make water. So water is a material which consists of 2 elements, or in this case, it's 2 components. So the material we call water, give it a pointer name H2O. And the arguments here, once again, for the material is a name, so call it what you like. And then the density has to be entered, and then the number of components, or the number of elements. So in this case, 2 elements. And then you have to go and specify how many of each element is to be used in the material. So we've defined the material, we have the pointer to it. So we use that pointer to say add the element hydrogen and add 2 of them. Then we go through to the next element and say add the oxygen, add 1 of those. So this particular constructor is using integer numbers of elements, and so now we're talking about molecules. But we don't have to have an integer number. We can mix things together. So these can be floats. Let's look at something more complicated. So a mixture could be an alloy or something like that. And let's make some aerogel. So now we have 3 materials. We're going to have some elemental carbon, we're going to have some water, and we're going to have some silicon dioxide. So we define the 3 elements that we want, and then we go ahead and establish the densities for the material. So aerogel is one of these nice low-density materials, and it is 0.2 grams per centimeter cubed, but you can change that, of course. And it has 3 components. One of the components is an element. The other 2 components are materials, and you can have these mixed up any way you like. Now, because we're no longer dealing with combining integer number of things, we have to define a floating point number. So we call this, for example, fractional mass. And our new material, which we're going to call aerogel, has this density 0.2, and it has a number of components, 3. But now this part is different. So when we start adding materials to this aerogel that we're creating, we have to have some floating point number here in the final argument. So in this case, we use 62.5%. So Geant4 has percent defined, but you don't have to use that. You can just use 0.625. Put that argument in, and so that's how much silicon dioxide you have. And then the next step is add the water. So that's 37.4%. And then finally, you add a little bit of carbon, it's 0.1%. So now we have a material which is aerogel, and now Geant4 knows what density is this material and what elements are in the material, and it can do what it needs to do with the tracking. So the element, by default, has the natural isotopic abundance. So if you don't care about isotopes, you just want the element that you dig up out of the ground, then use the defaults, and you don't have to worry about defining the elements. So this is what you get, even though the gram per mole value is different from the natural abundance. As I mentioned before, the hadronic code only knows how to deal with specific nuclei. It doesn't know about elements. It only knows about isotopes. However, if you don't like that, you can change it. So now you can define an element which has a non-natural abundance. One good example would be enriched uranium, for example. So we start with an element. We can define our own element, but we make it out of a list of isotopes. So let's go through the exercise of making some nuclear fuel. Okay? So we start with an isotope, U-235, 92 protons. Total number of nucleons is 235. And here's the grams per mole, 235.044. And U-238 is 92, and A equals 238. So now we have defined our isotopes, and we have the pointers to each isotope. Now let's put these together and make the element, which we will call enriched uranium. So now we've got the isotopes. Our new element is going to be called enriched U. And it has 2 components. In this case, the components are isotopes. So to this element, we go ahead and add the isotope U-235, and then we add the isotope U-238, and then you can decide what percentage or enrichment you want for the particular isotope. So here we've got 5% U-235 and 90% 238. And now we can go a step further and make some uranium hexafluoride. And so for that, we need some fluorine, so we go back to the element. And here we're using the standard element definition of fluorine. Z equals 9, A equals 18.998 grams per mole. So we've got that. And now we make the material nuclear fuel, which is actually uranium hexafluoride. So, nuclear fuel density is about 5. And here it starts to get interesting because this gets a little hot, so we can define the state as a gas. And the temperature is 640 Kelvin. And the pressure is high. So we've got something which is pretty non-standard as far as temperature and pressure. Now, we have created, on the previous slide, we've created the There we go. We've created the fluorine, and we want 6 of those. And we've created the enriched uranium, and we want 1 of those. So now the fuel consists of uranium hexafluoride. Now, as I mentioned, the entries in red, these state, temperature, and pressure, these are all optional. So if you don't put these in, you'll get standard temperature and pressure, and at least for the case of nuclear fuel, it won't work. And because neutrons are important, if you're doing this kind of thing, the temperature is very important. So if you're doing neutron stuff, you have to be careful that you set the temperature. Otherwise, the results will not be correct. Now, finally, we come to the easy way. So the National Institute of Standard Material Database is encoded in a class in Geant4, and this has most of all the materials that you'll want. 3,000 isotopes are defined. All of the elements, however, are of natural isotopic abundance. So if you want something which is not natural abundance, you'll have to define it yourself, but everything is there. So Geant4 has included these predefined materials for you to use, and if you want to find out how these are arrived at and what they are, you can go to this site and check that out. But there's a very good reason for using these. These provide the best accuracy for the major parameters. So these are all well-measured materials. The density is very well understood. The isotopic composition is very well understood. Especially important if you're doing, for example, medical studies and you want to know that you're using exactly the right human tissue analog, for example, then you'll use the standard from Nist. And that way everybody knows that you've defined your element properly, or your material properly. So it has the correct composition of materials, it has the correct ionization potential, it even has the chemical bond information. It has elemental materials up to californium, tissue equivalent plastic, as I've just mentioned, dry air at sea level, many other standard things that lots of people use. High energy physics materials are there, lead tungstate, for example, liquid argon, all defined. If you're doing space research, then we have the materials like Kevlar and Dacron, they're defined. And a lot of biochemical materials, so adipose tissue, components of DNA, proteins. A lot of these things are already read. So I mentioned about 3,000 isotopes, but also 315 materials defined so far. So how do you put this in your code? First thing you have to do is get an instance of this thing called G4 Nist Manager. So in C++, we call this a singleton class. There's only one instance of it. And what you have to do to get a pointer to it is just do G4 Nist Manager : instance. That just returns a pointer, and now you have access to this manager. And then you can do everything you need. So you have the manager and say, find or build this element. So you put in a chemical symbol, and you'll get that element. Or if you know what the Z is, put that in, and you'll get it that way too. Similarly, you can find materials. So put in aerogel here, and you would get a pointer to the aerogel material, and then you could stick it in your geometry, and you'd be all ready to go. So lots of good options, and probably the best way to go if you want to make sure you're using everything in the standard way. Now, how do you know what's already in here to choose from? You're going to have to find that out. And so we have a line in the user interface command in Geant4. So if you're, when you did your hands-on exercise yesterday and you looked through the help list of commands, maybe you want to try it today by looking at material/nist/print element or list materials. And then you can find everything that is listed and available for you to use from the Nist database. So that's it for materials. We talked about how to define things right from the isotopes on up to materials, and these are the class names: G4 isotope, G4 element, G4 material, and how to set the material conditions. So you can set density. This is required in all cases. And the optional parameters are state, temperature, and pressure. But whenever you can, try to use the Nist database materials. So they're the most accurate and very well standardized. Are there questions? Okay.
Your slide number 6. So if you use this standard galactic, this is hydrogen, right? You put for the
That's hydrogen at,
hydrogen.
yes.
So if I want to make a more realistic beam pipe,
Then you would define air.
nitrogen, for example.
Or you could define nitrogen or air and just say low pressure.
Okay.
Yeah.
So you put air and then
And then set the pressure to, density has to be very low, yeah. Yeah. Yes?
Supposing you were defining a material by defining a mixture, you have to define the number of elements.
That's right.
Is that somehow dynamic during the simulation, or is this static?
It has, once you've defined it, it always stays the same during the simulation.
so it's not sensitive to, let's say, radiation damage. It's
No.
not going to change.
It's not going to change the composition during the run.
Or supposing a nuclear decay, the materials stick the same.
The material stays the same even when you have a nuclear decay, yeah. Yes? No, in this case, percent only means parts in 100. So it's a very trivial definition and it doesn't have anything to do with... You will have to figure out whether you want to use by mass or by volume. But this one is by... Let's see, where did we use that? Ah, here. This is by mass. Yeah. If you want to do by volume, you'll have to make a calculation. Yeah.
Is there an alternative to define this in a fraction of atoms?
Oh, if you want to define, you can't define it by fraction of atoms, no. But you can, for example, if you're defining a molecule, then you just have an integral number of atoms.
Yes, you can. Like silicon dioxide, you can. But then you cause the second argument is not the double, but the integer.
Yeah, so if we would do that the same way, for example, as we did H2O. Yeah.
If it is integer, it's just number of atoms. If the argument, the method name is exactly the same. If the second argument is double, then it's a fraction of atoms.
Okay.
Okay, bon dia and good morning. And so this is the first of 4 geometry talks. And the geometry session is one of the fun session because it's quite easy to understand and you don't really understand what you're doing. And as soon as you do something, you really see it. So it's very nice part. So I start with the general concept of how you define geometry, given you have already known how to create materials. Okay? Then this is the class, is the mandatory class. That in this class you define geometry. Okay? So that is something you have to implement by yourself, no exception. And then let me start with the basic concept of Geant4 geometry, one by one. And in this talk, it takes 1 hour, a bit more than 1 hour maybe. And just to go through very basic of the defining geometry. So by end of this talk, you can define a few simplest geometries. Okay? So let me start. introduction. So geometry, we have 3 different classes to define geometry. I don't know which is the bottom or top, but the baseline is solid, what we call solid. That represents the shape and size of the shape. So it could be a box of 1 meter height, 1 meter width, 1 meter wide, 2 meter deep, 3 meter high, or something like that. It just say you are going to define this kind of shape with this size. Okay? The second layer is what we call logical volume. Here, most important information is material. So you say, now this is the box, but not the box, but it's made of lead or water. Okay? So now this is not a conceptual box, but it's really something made of material. And the very bottom layer, physical volume. Here you define position rotation. Unless you define where it is, it does not make any sense. So the shape, material, and the position. The reason why we have 3 different layers is the following. Suppose you are going to implement a crystal calorimeter. All crystals are the same size, same shape. Then you have to create only one object of this box. You define only one logical volume, that of whatever the crystal material. But you may need thousands of physical volume to locate each crystal one after the other. Okay? But with these 3 hierarchies, at least we can reduce quite a bit of objects. If you have only one class that have shape, material, and position in one class object, you have to have millions of same objects. But in this case, you only need physical volume. Got it? Okay? This is the most basic concept we have to share. And this diagram is so-called UML, Unified Modeling Language or whatever diagram. And box represents a class. Okay? And this diamond said that this logical volume class has something about solid. So this one has that one. Okay? In this case, logical volume, we need to know what the shape is. Okay? So logical volume has the information of solid. Okay? And this symbol looks like arrow, but it's not an arrow. So box is a kind of solid. Okay? Tube segment is a kind of solid. Okay? So this mark is a kind of. Okay? And this mark is has. So this guy has that guy. Okay? So we did it in this way. So here, solid could be, in reality, it could be a box or a tube or whatever, the variety of different shapes. Okay? But they all are a kind of solid. Okay? The logical volume, logical volume need to know the solid and also the material. Okay? Okay? And physical volume, there are quite different physical volumes, concrete classes. I'll discuss only this one within this session, but I'll discuss much more about all other options, much more clever way to define the positions in my second talk in geometry. Okay, got it? Yeah. As far as you understand this concept, you are almost done. It's very simple. Okay. So here is a bit of code. Basic strategy is that first you define a solid. Okay? In this case, it's a box. But given a box is a kind of solid, you store the pointer as a base class. Okay? And here you said 1 meter, 2 meter, 3 meter. But I'll come back to this in a few slides. It's half width. So in reality, you are saying it's a box of 2 meter wide, 4 meter deep, and 6 meter high. Okay? But it's still a box. You don't know what it is made of. The next is logical volume. This is a constructor. But for the case of logical volume, there's no derived class. It's always logical volume. There's no other class. So it takes, first of all, the pointer of the solid. So now it knows what the shape is. Okay? Then the material. Assuming that you have already defined this material. Okay? And you need a name, and just leave them for zeros. You don't need it. You don't need them at all. Okay? Now you know this box is not a conceptual box, but it's made of water or whatever, iron, whatever. Okay? Now you press it. Here's a physical volume. This should read physical volume placement. So you really press it. Okay? With rotation and 3 vector, that is position x, y, z. And logical volume, of course. And name and mother logical volume. That means you have to say in which mother volume you are placing this guy. Okay? And copy number, because you may have more than one. So start with 0 and just add increment. Or I don't know what happens if you have negative numbers, but if you don't, we don't care if it is sequential or not. So it may be a good idea to have, let's assume we are implementing this classroom. Okay? I don't know how many chairs, but at least obviously there are 2 sections here. So the copy number of that side could start from 0 to 50, let's say, but this one does not have to start from 51. You may say 100, so that you can clearly distinguish this section, that section. We don't care, okay? But we suggest you to use different numbers for each physical volume. Okay. Got it? So this is the basic strategy. So a volume is placed in its mother volume, okay? That means this classroom is the mother volume. Okay? And position and rotation of the daughter volume is described with respect to the local coordinate system of the mother, so this classroom. So the origin has to be somewhere in the middle of the classroom, okay? And I don't know which direction is x. Let's say x and y and z, okay? Then you say, if you describe this particular chair, you say it's here, x equals something, y equals something, z equals something. Okay. That's it, okay? Please, daughter volume cannot protrude, or in other words, cannot go outside of mother, even partially, okay? Has to be entirely contained, okay? That is our rule, okay? So suppose these green dotted lines mother volume, okay, in this classroom, and you are going to locate this chair, then all you need is a position with respect to this classroom, okay? And suppose you are implementing this building, okay, not only this classroom, but all this building. You still don't need to locate this chair with respect to the global building, because you have already defined this classroom. So you define the position of this chair with respect to this classroom. Then sometime later, you should locate this classroom with respect to the big building. Okay? This is a hierarchical structure. Got it? Okay? So one logical volume can be placed more than once. Okay? One or more volumes can be placed to mother volume. So let me go back a few slides. Not that easy. Okay. Here, okay. So this underlined part, daughter physical volume. this is the information of the logical volume. So in this case, let's assume cigarette box. I don't smoke, but I always use this concept. It's easy to understand for everyone. Okay? Let's suppose a cigarette box. It contains 20 cigarettes inside. Okay? So suppose you have 2 cigarette boxes. They all are completely identical to each other. Then you have one solid that is the shape of the cigarette box. Then logical volume, cigarette box is, let's suppose it's made of air. Okay? Then you know where the cigarette box is. Otherwise, the smoker will be complaining. Okay? Then you place cigarettes in the box. Okay? But you are placing cigarettes to the logical volume. So once you define the cigarette box, this is always a cigarette box with 20 cigarettes inside. So you can place whatever the number of cigarette boxes one after the other. But suppose you have another cigarette box that is already opened and half of the cigarettes have already gone. Then you can still use the same solid because the shape and size of the cigarette box is still the same. But you have to have another logical volume because in this particular already opened cigarette box, you may put only 10 cigarettes rather than 20. Okay? Because the mother-daughter relationship is a concept that belongs to the logical volume. If the content is different, you cannot share the logical volume. In other words, if you share the logical volume, all the structure inside the volume are common to each other. Okay? Now, so let's go here. So logical volume can be placed more than once. Okay? So here's the mother volume. Okay? I put something in. You may also put the other one. Okay? And even you may put something else that is different shape or different material, whatever, in the mother volume. Okay? And now you define this classroom. Suppose there's another classroom, it's exactly identical. Okay? Then you place this mother volume twice, physical, placement. Then you don't have to place daughters for this one again because we share the logical volumes. Okay? If content is different for this third classroom, then you have to have different logical volume. Okay? So the word now we need to identify. We need to define what the word volume is. Okay? It must be a unique physical volume which fully contains everything. We don't allow any small piece or whatever corner that is outside of the word volume. Okay? Because once track comes to the boundary of the word volume, we understand the particle is gone. Okay? And for the case of other volumes, the surface of the mother and daughter can be touched. Okay? But for the case of word volume, it is not allowed. So please make the word volume slightly bigger than your detector or whatever. Okay? So this red one is the word volume. Now, the word volume defines the global coordinate system. That is the center of the word volume is the center of origin. And it defines X, Y, Z. Okay? Please note, position of a track is always given with respect to the global coordinate system. Even it's somewhere deep inside, for example, this blue box. It always say, I'm here with this green coordinate system. Of course, time to time, you need to know where this particle is in this local coordinate system. We offer transformation matrix. Okay? So please note the position position is always given. Not only the position, but momentum directions, everything of the particle always come in a global coordinate system. Okay? Any question up to now? Here, the conceptual part. Yes.
So, if I understood correctly, this word volume basically gives you the boundaries.
Yes.
Whereas so in briefly it could be a box of air.
Yes.
And you define that in that G4 volume, right?
G4 box, yes. Box. Then you have to have logical volume, and you have to have D4 PV placement. The position is 0. You cannot place to something else. Okay? Yeah. Okay. Now, use a detector construction. So I have already shown this in my first talk. Geant4 is a toolkit. It does not offer you any main. Of course, examples have main, but okay. And in addition to the main, you have to implement few classes that are mandatory. And let me repeat. We have two different kinds of user classes. The first is what we call initialization classes. They are invoked only at the time we initialize Geant4. For example, defining geometry, defining physics, kind of things. They are invoked only at the beginning of the simulation. While these action classes, they are invoked during the event loop. Okay? This run action is invoked at the beginning and at the end of the run. At the beginning and end of the event. Stacking action, I'll discuss it later. Then tracking, stepping, I have already discussed. Okay? So they are invoked at the tracking time. And given now we are living in the multi-threaded mode, they must be thread local. Okay? They are basically, they reside in a different thread working independently. So they must be thread local. Meanwhile, these are shared because physics is unique, common, geometry is common. Okay? That's the reason why we need this particular class, the third one. You have only one class object that takes care of instantiating these action classes per thread. Okay, that's it. So I'll come back to this later. Anyway, so we are now discussing about this guy. Okay. So user detector construction. It has constructor, destructor, and pure virtual method of construct. This is the most important method you have to implement because it's purely virtual. Okay? The other important method is construct Sdn Field. Okay, the construct method should return the pointer of the world physical volume once you create all of your geometry and material. Okay. The world physical volume represents basically everything. The detectors part and the field part should be described in this second method, construct Sdn Field, because detector has to be thread local. Otherwise, you are mixing hits of more than one event because each event goes to a different thread. That's the reason why we have two methods. This first method is something you describe. That's something that should be shared all over the thread. Okay? Typically material and geometry. Okay? While in this second method, you have to describe what you want to score. What you have to describe, this is my detector. Okay? And also the field, you may wonder why, but field can be dynamic. That means at a certain time, field is different from other time. So if you have only one field object, it doesn't work. Okay? So we need two methods. Okay? The distinction is whatever that should be shared should go to the first method construct. Whatever that should be thread local should go to the second method. Is it clear? Okay. Now, this is your class, my detector construction header file. And you have to include the base class, and you have to derive your class from this base class. So basically, you implement these two methods. Okay. And of course, there could be nice set methods, get methods, and whatever the private method, if you like, and data members must be needed here, depending upon your geometry. Anyway, so to describe your geometry, derive your own concrete class, like my detector construction, or Alice detector construction, or whatever, okay? Or a human phantom, if you like. Okay? That anyway it should be derived from this abstract base class of G4V user detector construction. Okay? And you do all these 8 things. Some are optional, as you see. Okay? Please note, the items written in black should go to the construct, while the items written in green should go to the second method of construct Sdn Field, okay? Because they are thread local. The first, as Dennis has already described, instantiate all the necessary materials. You can change material of your detector, whatever, after the first run. Okay? You can do it. But we suggest you to anyway instantiate all the potential materials you need at the beginning. You don't lose any, not much of memory, because we calculate cross-sections only for the material that appear in your geometry. Okay? Now you need to define all the shapes, okay? All the different shapes, and logical volumes, as we discussed, and physical volumes, okay, to create whatever, describe all the geometry. Then, if your detector or whatever has a magnetic field, define it in a construct Sdn Field second method. Then, sensitive detectors, scorers, if you use it not as a command-based scorer, but which we have already discussed, but if you have to define detector, that is something should go in this second method. Okay? And it would be very nice if you change the colors of each detector component. Okay? That should go to the construct. And region that I'm going to discuss later should go, this still belongs to the geometry, so it should go to the construct method. Okay? Okay, any question up to now? Okay, let's go to solid. Okay, solid and shape. I don't expect you to read these small characters, no. And anyway, here's G4V solid, and here's the G4, another layer of the base class, and then here the box, cone, para, tube, or whatever, all different shapes. That means, anyway, all shapes are derived from G4V solid. That is the only information I'd like to transmit with this slide. Okay? So, and it defines as a base class the concept of solid in terms of Geant4. Or concept means what should be the behavior of a kind of solid. Okay? So compute distances between the shape and the given point inside or outside, or check whether a point is inside the shape or outside the shape or on the boundary, or compute the extent of the shape, or compute the surface normal if the particle is on the surface. Okay? So if you have very nasty shape that Geant4 predefined, none of Geant4 predefined solid can describe, you can create your own shape by implementing all these kind of methods. Okay? For example, Atlas, the famous accordion calorimeter, they first tried all different pieces one after the other. It blew up memory. Then they start to use the Boolean operation. Now it was ultra slow. So they ended up creating its own Atlas zigzag shape, implemented, and it works. So if you have any nasty shape, you may do it. But nowadays, we also have Boolean operations that is well tuned. So I'll discuss it later, anyway, within this talk. The solid. We have a few different categories. First is CSG, constructed solid geometry. It's a box or tube segment or cone segment, trapezoid, and so on and so forth. Okay. The second category is what we call specific solid. So the usage is quite similar to the CSG. You can define the size. But the implementation is almost like a boundary representation. We also have tessellated solid. I'm going to discuss this later. And Boolean operations to combine the shapes. Okay. So first and the simplest is a box. So it takes 4 arguments. The first is the name, then half x, half y, half z. The reason why we chose to use half width is the following: that, as you see here, this box here, x is here, it goes plus minus 40. Okay? Because origin is always in the middle. So keeping the value 40 is more convenient for calculation rather than keeping 80 full width. Okay, that's the only reason we chose this way. Okay. Now tube segment. It takes these parameters, 6 parameters basically: name, inner radius, outer radius, then the half height. Note that this is radius, not diameter, so it's already in half. Okay. And then half length, then starting phi, and the span. If you want to define full tube, this should be 2 pi or 360 degree. You anyway multiply the unit so that it's okay. You may say 2 pi radian or 360 degree. Then it's okay. And so on and so forth. There are tons of different shapes. Some of them I've never used, I never could understand. Okay. I invite you to look at this section of Geant4 Application Developer's Guide. And if your browser has Java installed, if you can click the shape, then Java window pops up, and you can rotate and play the shape if that helps you understand the shape. Okay. And one comment here is we have 2 spheres, G4 sphere and G4 orb. G4 sphere is the full spec sphere, so that you can define inner radius as well. And you may slash it if you like. Okay? Could be a half a sphere. G4 orb is much simplified. You cannot define any inner radius. It's really a full sphere. Okay? But still, we have already learned you can put a daughter volume inside. So if once you use this, but you still need to define a shell, create a daughter volume that is smaller than the mother, and make it made of air. Then you can press it inside. Then it's really a shell, right? So this is faster. The only case you have to slice it, you definitely need to use sphere. Got it? I believe I can use the white blackboard, right? So there are quite often frequently asked question. If you have an empty box made of paper and filled by air, how you define this box? There are several different ways. Oh, yes, it is. Okay. Now, this is the empty box. The box itself is made of paper, let's say, but filled by air. How can you define this volume? Okay. The naive way is, in the box, you don't have inner surface. So, naive concept is creating this plane, other plane, and so on and so forth, you combine. But you don't have to do this. Instead, create a box that is made of paper and create a smaller volume, slightly smaller than this box, make it made of air, and use this place inside this matter. In this case, this part is not a mixture of air and paper, but it really override so that this part is made of air. Okay? Yes. You have to define two volumes, two solids, and you need to have two logical volumes. And this is the mother, this is the daughter, so it's really a placement. Of course, there's the other way, there's the Boolean operation. But this, as far as the tracking, navigation is concerned, this is the fastest. Okay? Okay, thank you. So, as I said, I really invite you to go to our user's guide and click and see. Okay? Now, specific CSG solid, the second category. The good example is G4 polycon, okay, like this. Okay? It takes name, then it's kind of cylindrical, so that it takes starting angle and span. We already discussed like a tube. Then here, number of node. Then R and Z of each node. That is, for this shape, we define 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 nodes. Z-axis is along this way. Okay? So we say we have 13 nodes and say that the radius and the position along Z-axis for each node. So here's node number 0. Okay? Suppose Z is suppose origin is somewhere here, then this should be plus something as a Z, and the R is 0. Second node is here, that is slightly larger in Z, and R should be something, this size. And so on and so forth. Once you define all the 13 nodes, we can define this shape. Okay? This is P-con. And actually, P-con, this kind of specific solid, the performance is improved quite a bit recently. And if you use the new solid or so-called Vecgeom libraries, particularly polygon performance is ultra improved. Okay. So we invite, for example, I think it's CMS who got a really boost because they overuse polygons. Okay. So there are a lot of different shapes I could never ever understand, except this tetrahedra. That is simple. Okay. Yeah, I cannot tell the difference between these two. Anyway, so if you go to the next section of the developer's guide, if your browser is Java enabled, yes, you can see it.
The previous slide,
Yes.
the reference of the coordinates on this hallway is in the...
Somewhere you said 0. Yes.
Yeah, it's right in the corner.
No, you define. Because you say where is the Z of the first node. If it is, let's say, 10, and Z is along this way, so somewhere here is the origin. You know. Sorry, just a second. Just waiting. Any question? Here, please, once you implement something, please visualize it first to see it, if it is not nasty, okay? And to visualize whatever the nasty shapes, you have to use ray tracer. Some other visualization drivers may not correctly visualize funny shapes, but the ray tracer always visualize as is, because it uses Geant4 tracking, so that it really visualizes what Geant4 particle will see. Okay. Now, tessellated solid. Tessellated solid is something that you define facets. Each facet could be either triangle or quadrangle, okay, like square. So if you define all the facets properly, you can define the shape. That's it, okay? And this actually is often used by CAD system. So this is so that you can really import all the facets of tessellated solid from CAD system, and you can use it in Geant4 if you have very funny shape. Okay? And also, given it's a class, you can define facets by hand if you want. For example, if you define the square, 6 squares one after the other, you can define a box, right? Of course, no one will do it, but you can if you like. Okay. And when you define the facets, please careful the order of the points. If it is screw-wise, so this is the outside if you define this way. Like screw. If you go this way, that side is outside. Okay? So if by any mistake one of the facets go flip, we cannot simulate because we cannot tell which is outside, which is inside. And also, we don't allow any facet missing because we cannot tell if this is inside or outside. Okay? This kind of hole is okay as long as you have facet here. Okay? Got it? So, for example, this is one solid. I don't know how many facets it has, but it's a really serious module of ESA which is already launched into the space. Okay? And this one is LHCb at CERN, and tracking the module. It has millions of facets. And in the past, we'd say, don't use it, or use it only for demonstration purposes because it's slow. But it's no longer the case with new solid libraries since 10.4. The speed up is here, okay, compared to the previous versions. 3 order of magnitude faster. So now you can really use it. And the LHCb is quite happy about this. Okay. So millions of facets is okay now, okay? As long as everything is correct. There's no missing piece or flipped piece. Everything is okay. Any question? The next is Boolean operations. We have 3 Boolean operations: union, subtraction, intersection. Union is addition, okay? And subtraction is digging. And intersection is cut out, basically overlap. And each of these operations requires two solids to operate, okay? And optional transformation if it is dislocated. Okay? And the second solid is positioned with respect to the coordinate system of the first solid. And result of the Boolean operation becomes a solid again. So you can do yet another Boolean operation if you like, to combine things one after the other. Okay? And please note that this special case of Boolean operation, suppose you combine these two. The origin of combined solid is still at the origin of the first solid. Okay? This is our notation, regulation. Okay? It's not somewhere in the middle, but it always the center of the first solid. Okay? If you have to add one more solid, like at here, let's say, then you have to say this is the position is from here rather than somewhere here. Okay. For example, this one. I started with a box, added a sphere here, and big sphere, slightly larger sphere here. Okay. And to visualize this kind of Boolean shapes, you definitely need to use the ray tracer. Okay. That Mihari has already described, I believe. So here's an example that says I combine box and cylinder or whatever. So just for fun, okay? And new thing here. In the past, we said, don't overuse Boolean operation because if you have 100 operations, it is 100 times slower. But it is no longer the case. In the past, the performance is really blue line, it's really linear. It's a number of the node, number of the primitives, it's a performance. Now this is here, okay? It's log of number of nodes. So it's basically constant. So this multi-union is a new operation that you may want to use a lot rather than Boolean operations, okay? Except for the case you combine just 2 or 3. In this case, the original old good days Boolean is faster, okay? Only for the first few. But if you go beyond 5, you should always use unions. But unfortunately, this works only for unions, solid. It doesn't work for subtraction or intersection, okay? Now I tell you how. Multi-union. You create multi-union. It's still a solid. This is multi-union. It's still a solid with a name, no other argument. Okay. Then it just defines the coordinate. So in the for loop, for each of these nodes, this should be small I. Maybe it's just capitalized because of the space or whatever. So you define box or whatever the shape, solid, and 3 vector and rotation matrix. This should not be 3 vector, this should be rotation matrix. I'm so sorry for that. Anyway, then transformation, add node. So you now have one box here. And so on and so forth in a loop, you combine. And once you are done, say, boxerize. That will actually really combine the things. So you now have one solid of quite nasty shape. Got it? Of course, these boxes could overlap or should overlap. Yeah, of course, there could be a separate part if you like. No restrictions. Because you are creating a solid. Given this is a solid, you can use it to create a logical volume to define a material, and you have to place it. Okay? Any question? Now solid is over. Okay? Yeah, this past 20 minutes maybe, I was just discussing about the shapes. A lot of different shapes. Now the logical volume. So logical volume, there's no derived class. It's always logical volume. It must take solid pointer. It must take material pointer that has already been defined. And the name, please. Okay? And they are basically you don't need to specify because by default they all are 0. Okay? So it contains all information of the volume except position rotation. That should be defined in the physical volume. Okay? The shape and dimension through the logical solid and material through this pointer. Okay? And in addition, sensitivity visualization attribute, that means colors or line style, could be associated to logical volume. That I'll discuss it later. Okay? So physical volumes of next type of the same type can share the common logical volume. Okay? So when we describe this classroom, you may create only one logical volume for one chair. Then we place it 100 times one after the other. Okay? So the pointer to the solid must not be null. There must be a solid. Okay? And the pointer to the material must not be null. For tracking geometry, I discussed this in my last talk in geometry, the ghost world or parallel world, whatever you may call. Okay? So this class does not meant to act as a base class. It's a concrete class. You always have to use this. Okay? So in addition, we do have a couple of service methods. The first is get cubic volume. This will give you the volume, not the shape, but the actual physical volume of the volume. The word volume has two meanings, It's not easy. So if you ask this method to a kind of simple solid like a box or cylinder, we know how to calculate the volume. So you always get the correct value or exact value. But for this method is the virtual method defined in the base class of G4V solid. That means it works even for the nasty shapes or Boolean operations or tessellated solid. So if this method is invoked for a shape that is combined by Boolean operation or whatever, we do Monte Carlo here. That means we shoot random positions, okay, and try to measure the volume. Okay, that means depending upon the random number sequence, you may get slightly different value. There's one hypernuance argument in quite some years ago, complaining he was measuring the volume of very nasty shape, complaining every time he asked, he got a different number. Yes, by nature, because we are shooting random numbers. Okay, but you still get something. Okay, and get mass method is also quite useful. It gives you the mass of that solid. If you have daughter volumes inside, it calculates the daughter volume weight as well. So if you have world volume of, let's say, Atlas, you can ask, get mass. It will tell you how heavy it is, the Atlas detector is. Okay? And we often use this method when we model the satellites. If that value is different from the original design, that means we make some mistake. Okay? So it's good if you try this method at least once. It gives you all the content inside and all total mass of the that takes into account of all the daughters inside. Okay. Any question for logical volume? This part is simple. Now region. it's a kind of concept, okay? The region is, each region, a region is a part of your detector or part of your geometry, okay? Each region may take different production threshold. Production threshold itself was already discussed by Mihari or Dennis, I don't remember, okay? So for example, you have a big concrete field. You don't need to care the tiny delta rays produced in the concrete field because you never see. In this case, you can set much higher production threshold for this concrete. That gives you much faster simulation because we don't generate any tiny secondaries in this concrete. Got it? So we can use region in this way. And a lot of other use cases, but the number one use case is always this production threshold. If you want to change the threshold from the default to the specific one that is unique for that particular portion of your geometry, you define the region, and you define the special production thresholds for that region. Okay. So suppose, I don't know why this color is changed, but anyway, this is world volume. Okay. It always take the it always is regarded as a default region. You cannot define region to the default region. It's already there. And when you naively define production threshold, that production threshold is associated to this default region. Okay? Now you put something. It still belongs to the default region. No, but unless you really say this is region A. Once you say this is region A, this belongs not to the default region, but this area belongs to region A, so that you can define different production threshold. And all the volumes inside share the same region. Okay? Unless you say here this is region B. Then you can specify yet another, production threshold if you like. And whatever the content inside, share this production threshold, not that one, or not default one. Okay? And please note that region concept, region information belongs to the logical volume. So if you duplicate this volume here, you are creating two areas that belongs to the green regions. Okay? Also, please note that if you, of course, for the default region, it's mandatory. You have to define default production threshold. Yes. And let's say you define something different for production threshold for region A. That's okay. And you don't specify anything for region B. In this case, this is our notation. This region B will not inherit the production threshold of region A, but it uses default. Okay, that is our notation, please. Please take a note. Okay. So to create a new region, it's easy. This is the region object with region name. And say this logical volume is a root logical volume. That means, for example, this box or this oval. Okay? Then whatever the daughter volumes inside belong to the same region. And for the example of the production threshold, you get the region object, create new cuts for whatever the cut values, and set to the region. That's it. Then that region has different production thresholds. This is absolutely beneficial if you have a big concrete or shielding that you never care of the tiny delta rays. This will really boost your simulation a lot. Okay. So production cuts or all other things which we are going to introduce. And in addition here, regional stepping action. In addition to the regular stepping action that is invoked for all the steps all over the world. You can specify a special stepping action for particular region, if you like. Okay? It's addition. Any question? Otherwise, the only thing you have to remember is we discuss it and in this slide. Okay? So when you really need to use region, come back to this slide. It gives you the information. So that's the only thing you have to remember. Okay? Now, physical volume. We have already discussed. This is positioning here. So in this session, I discussed only this guy. It's a kind of physical volume. Okay? So we have already discussed this basic strategy. Solid, logical volume, and physical volume. Okay? So before we go into the detail, Geant4 actually offers lot of different clever ways to describe geometry. The first thing we are going to discuss is just this one, okay? The placement volume. The other concept is repeated volume. So I'll discuss it much in detail in my next talk in Geometry 2. But suppose you are going to implement this classroom once again. You have 100 chairs. Okay? So in this way, you say, here's number 0, number 1, number 2, number 3. You create physical volume for each chair. So in the memory of the computer, it ends up with 100 objects of the placement. Okay? That is easy to understand, but memory-consuming way. Other ways make it a bit clever, that you create only one object of the chair, physical volume of the chair. This is intelligent, so that if you ask the position with copy number 0, it says, I'm there. If you ask the same chair with a copy number 51, that will say, I'm here. If you ask 100, it will say, I'm there. In this way, you have only one object in the memory, but by changing the argument, your copy number 1, 2, 3, 100, it answers different position. In this way, instead of having 100 objects in the memory, you have only one. Okay? So that is something we say repeated volume. So we discuss it later. Okay? Okay? Obviously, this requires much less memory. So if you have hundreds or thousands or millions of same kind of volumes, this is better. But within this talk, let's stick on to this first one. Okay, placement. Okay, one placement is really one chair. So here, this is the actual class G4P physical volume placement. This is a kind of placement. It takes transformation 3D, that is rotation matrix, and 3 vector, that is position. Daughter logical volume, its name, and mother logical volume. This many, please always say no. Yes, true is not supported. Sorry for that. And copy number. Unique 0 or positive integer, please. And I discussed this particular Boolean flag in my third talk. It's quite important, but for the time being, let's keep it false. Okay? Now, with this mother logical volume, you define the coordinate system, the mother. So, translation and rotation, you can really place this guy. That's it. Okay? And if you look at LXR code browser, you may have you will see other implementation. It's different. The first argument here is transform 3D, that takes rotation and translation. All the rest are the same. The second one, it takes bare rotation matrix and translation. Okay. It's a complication, I know. And the reason why we have this one is the definition of translation is the same, but definition of rotation is different. In this case, instead of rotating the daughter, it rotates the mother. So instead of rotating a chair, you are rotating the classroom. It's a nightmare. And it's not understandable for human being. But I don't know why, but a lot of CAD systems use this. That's the reason why we have it. So please don't use it. Please. Except you have no rotation. If you don't have any rotation, this is simpler because you don't have to go with these characters. Okay? So when you don't need rotation, and actually you see a lot of this constructor in our examples, but I guarantee all cases this rotation matrix is 0. Then this is simpler. Okay? That's it. So don't, once you rotate your classroom, it's a nightmare. You never understand. At least I never. Okay? That's it. So, of course, this is the very simplest thing. It's not enough for you to describe, for example, Alice detector or human phantom. But at least now I believe you are confident you can define a few very basic shapes, basic geometry, right? So let's try this out at Fun Zone today, this afternoon. Okay? And once you made just a few something, you realize it's easy and it's fun. Okay? Okay, you're done. Questions? If not, okay, yes, please.
Yes, if not.